Story of Fascia, From Neglected Tissue to Key to Health. Introduction. What is fascia? Fascia is a continuous three-dimensional network of connective tissue that surrounds, supports, and interweaves every structure in the body. In simplest terms, it is the body's packing material, forming sheets and webs of collagen fibers that wrap all muscles, bones, nerves, blood vessels, and organs. If we could magically unravel the fascial system from the body, it would form a single interconnected web with a surface area larger than the skin. For decades, fascia was thought to be inert tissue, the white stuff under the skin and around muscles, but modern science reveals that it is a dynamic organ critical to movement, sensation, and health. What does fascia look like? Under a microscope or dissection, fascia appears as thin, translucent sheets or filmy, cobweb-like fibers. It can be loose and stretchy, as in the areola or loose fascia that allows skin and muscles to glide, or dense and tough, as in aponeuroses, tendons, or ligaments. Multiple layers of fascia are usually separated by a slippery gel-like ground substance rich in hyaluronic acid that acts as a lubricant. This allows adjacent fascial layers, and the structures they encase, to slide smoothly over each other during movement. Specialized cells in fascia, fibroblasts, and the recently discovered fasciocytes produce both the strong collagen fibers and the slippery molecules like hyaluronan that together make fascia simultaneously tough yet flexible. In short, fascia is a unified organ system that interpenetrates and envelops all other organs, endowing the body with structural cohesion and an integrated environment for all systems to function. Early anatomical neglect of fascia. Historically, anatomists paid little attention to fascia. In classical dissections, fascia was the annoying, clingy substance you had to cut through to see the important parts like muscles, organs, and bones. The 19th century anatomist Erasmus Wilson famously described fascia as a mere natural bandage, observing that cadaveric fascia looked like sticky white sheets that hold the body together. Because these fibrous sheets obscure other structures and can seem messy, generations of medical students were actually taught to slice away and discard fascia. As one modern manual therapist quipped, "In your first year of medical school, the fascia you can throw in the garbage can. We are trained not to pay attention to it." In other words, well into the 20th century, fascia was dismissed as the packaging around the real functional tissues. This neglect meant that for centuries fascia received scant scientific study. Even basic questions, such as whether fascia contained nerves or could contract, went largely unanswered. It wasn't until the late 20th century that a few pioneers began to ask if fascia might be more than just passive wrapping. Notably, Dr. Ida Rolf in the mid-1900s proposed that manipulating fascia could improve posture and health, founding the field of Rolfing, or structural integration. Osteopathic medicine, since Andrew Taylor still in the 1890s, also held that fascia plays a crucial role in the body's unity and self-healing. Still wrote that when treating patients, you are doing business with the branch offices of the brain by working through fascia. Such ideas, however, remained outside mainstream science for decades. The rise of fascia research and recognition. Around the turn of the 21st century, fascia finally started getting serious scientific attention. In 2007, the first International Fascia Research Congress was held at Harvard, a landmark event where anatomists, biomechanists, and clinicians convened to discuss the Cinderella tissue that had been ignored for so long. Over subsequent years, research into fascia exploded. By 2017 to 2018, fascia was being re-evaluated as a critical system. Some researchers even suggested classifying the body-wide fascial network as an organ in its own right, potentially the largest sensory organ of the body. While it's debatable whether fascia meets the technical definition of an organ, these discussions underscore how important this tissue is now believed to be. Fascia research has produced a wildfire of new insights that are challenging conventional belief about how the body works. One watershed moment came in 2018 at the Fascia Research Congress in Berlin, when anatomist Carla Stecco announced the discovery of a new cell type in fascia, more on fasciocytes later. Around the same time, using new imaging technologies, researchers like Dr. Neil Thies observed novel fluid-filled fascial structures, dubbed the interstitium, that suggested fascia constitutes a previously unrecognized anatomical system. These findings, alongside accumulating evidence linking fascia to chronic pain, sports performance, and even immune function, have cemented fascia's status as the hot topic in anatomy and physiology. What was once thought of as irrelevant gristle is now appreciated as a complex, vital tissue, one that connects and communicates throughout the body. The Body Mechanic is a wellness and fitness studio in Cary, North Carolina, led by coaches Jeff Wooten and Kimberly Weber. Unlike most studios, they recognize fascia as the body's hidden network that profoundly influences movement, strength, and recovery. By incorporating specialized techniques designed to reduce fascial tension and restore lubrication between layers, they address problems that are often overlooked in traditional fitness and wellness approaches, helping clients move with greater ease, less pain, and more resilience. Fascia's change in status. While until recently considered unimportant, fascia is now acknowledged as the biggest organ in the body, and perhaps the most important one. The Fascia Guide, 2018. Not everyone agrees on calling it an organ, but this statement reflects the newfound respect for fascia. A body-wide network, fascia everywhere. One reason fascia is so important is that it literally pervades everywhere. The official Fascia Nomenclature Committee defines the fascial system as the continuum of collagen-containing connective tissues that permeate the body, surrounding all organs, muscles, bones, and nerve fibers, endowing the body with a functional structure and providing an environment that enables all body systems to operate in an integrated manner. In practical terms, this means from head to toe, inside to out, everything in your body is linked by fascia. To understand how pervasive fascia is, consider the following examples. Muscles. Every muscle fiber is wrapped in a fine fascia called endomysium. Bundles of muscle fibers, fascicles, are encased in perimysium. An entire muscle is sheathed in epimysium. These layers are all connective tissue fascia, and they not only protect and separate muscle fibers, but also transmit force between them. When your muscle contracts, it pulls on these fascial layers, which in turn merge into tendons, continuous bands of fascia that attach muscle to bone. Nerves. Similarly, every peripheral nerve fiber has a delicate collagen casing called endoneurium. Groups of nerve fibers, fascicles, are bundled in the perineurium, and the whole nerve is covered by the epineurium. These are fascial layers of the nervous system. They provide both support and nourishment, housing tiny blood vessels and immune cells, and allow nerves to slide smoothly as our joints move. Notably, these nerve fascias are innervated by nervi nervorum, nerves to the nerve, which can cause pain if a nerve's sheath is inflamed. Bones and joints. All bones are wrapped in a tough fibrous fascia called periosteum, and even the cartilage on joint surfaces has a surrounding fascia, perichondrium. Joint capsules and ligaments are thickened specialized fascia that hold joints together. When you crack a joint or feel stiffness, the sensations come partly from these fascial capsules. Blood vessels. Every blood vessel is encircled by connective tissue, tunica externa for arteries, veins, which is essentially a fascial layer helping give the vessel structure. Larger vessels often travel through fascial planes. For instance, the carotid sheath in the neck is a fascial tube containing the carotid artery, jugular vein, and vagus nerve. Even the heart is contained in a fibrous pericardial fascia. Organs. Each organ in the body cavity is enveloped in visceral fascia, e.g., the lungs in pleural fascia, the heart in pericardium, the abdominal organs in layers of peritoneum. There are visceral ligaments, fascial bands that tether organs in place. For example, the ligaments that suspend the liver or uterus. The mesentery that supports the intestines is a double-layered fascial sheet that not only anchors the gut but carries blood vessels and nerves to it. In fact, thin connective tissue layers line almost every internal surface. By one broad definition, Fascia includes all the collagenous connective tissues that cover, divide, and penetrate every region of the body, from the epidermis to the tissue covering every nerve, endoneurium, perineurium, epineurium, to the tissue permeating voluntary muscles, endomysium, perimysium, epimysium, to the visceral organs and ligaments, and even the dura mater around the brain. In other words, fascia forms a continuous net that literally holds us together. Key point: fascia isn't a single organ like the liver or heart. It's more like a universal fabric that connects all parts of the body. The fascial network provides structural continuity. When you tug on one corner, the tension can transmit far away. This is why an ankle injury might later show up as knee or hip pain. The fascia has reorganized tension along the line. It's also why therapists talk about fascial chains or meridians, linking, say, the soles of your feet to the top of your head. As one researcher put it, fascia is almost 1/3 of our biomechanics. The fascia enables different muscles and tissues to coordinate and share loads across the body. Without it, our muscles would have to work in isolation and our organs would flop around. With fascia, everything is unified in function. Fascia's role in supporting internal organs. Fascia not only surrounds muscles and bones, it also supports our vital organs in subtle but crucial ways. Within the chest and abdomen, layers of visceral fascia line the cavities and wrap each organ, both suspending them in place and allowing for necessary motion. For example, the lungs are each encased in pleural fascia that lets them glide smoothly against the chest wall as they expand and contract. The heart sits in the pericardium, a fibrous fascial sac that anchors it to the diaphragm and sternum so it doesn't bounce around with each heartbeat, yet contains a slippery serous lining so the heart can beat friction-free. The liver, stomach, and intestines are attached to the abdominal walls by peritoneal fascia, the mesenteries and omenta. These attachments, once thought insignificant, actually form a continuous pathway for blood vessels, lymphatics, and nerves, and keep the organs properly oriented. In 2017, the mesentery itself was reclassified as a continuous organ structure, highlighting the importance of this fascial support. Fascia around organs often creates distinct compartments. For instance, the kidneys are wrapped in renal fascia that holds them against the back muscles. If that fascia loosens, such as in extreme weight loss, a kidney can actually drift downward, a condition called nephroptosis. Visceral fascia can also compartmentalize infection or inflammation. An abscess in the appendix, for example, might be walled off by surrounding peritoneal fascia to protect the rest of the cavity. Crucially, fascia enables organs to move in harmony with posture and breathing. When you bend over or twist, fascial connections ensure your organs shift without tugging harshly on nerves or vessels. The fascial layers between organs, filled with lubricating fluid, allow the stomach to slide over the pancreas, or the loops of intestines to glide over each other as our body moves. Even small motions, the heartbeat, lung expansion, gut peristalsis, require that organs have some play within their fascial envelopes. Stiff or adhesed fascia can impair these motions, contributing to conditions like restrictive lung disease or digestive motility issues. Finally, fascia provides pathways for circulation and nerves to reach organs. Blood vessels and lymphatic vessels are often sandwiched in fascial planes. For instance, the intestine's blood supply runs through the mesentery. Nerves, too, follow fascial planes to penetrate organs. Therefore, healthy, flexible fascia is essential for unhindered blood flow and nerve communication to the viscera. For example, the lymphatic system, which drains interstitial fluid and is vital for immune function, relies on fascia and muscle movement to pump lymph. Tiny initial lymphatic vessels are tethered to surrounding tissues by collagen fibers. As fascia and muscles move, these fibers pull open the lymphatic capillaries to allow fluid entry. If fascia becomes too rigid, such as scarred or fibrotic, it can impede this natural pumping mechanism, leading to swelling or poor tissue detoxification. In summary, fascia is the often unseen scaffolding and lubricant for our organs. It keeps each organ in its proper place, yet with the freedom to function. Visceral manipulation therapists, who manually work to loosen fascial restrictions around organs, report that releasing an adhesion on, say, the liver can improve shoulder range of motion or neck pain. This again underscores that through the fascia, everything inside is connected. Fascia as the hidden sensory organ. One of the most surprising revelations of recent research is that fascia is richly innervated and may be our largest sensory organ for body awareness. In fact, fascia has 6 to 10 times more sensory nerve endings, mechanoreceptors and other receptors, than the muscles do. Traditionally, anatomy taught that muscle spindles were the main proprioceptive sensors for position sense. We now know that the extensive nerve network in fascia plays an equal or greater role in telling the brain what the body is doing. Some scientists have estimated that an adult's fascial system contains around 250 million nerve endings, on par with, or even more than, the skin. No wonder some call fascia our internal sensory organ for posture and movement. What kind of receptors are in fascia? Multiple types of mechanoreceptors and nerve endings have been identified in fascial tissues, each sensing different stimuli. Then Golgi tendon organs, Golgi receptors. These are found near muscle tendon junctions and in ligaments. They detect high levels of tension. When stimulated, for example by a strong stretch, Golgi receptors trigger a reflex that causes muscles to relax, protecting them from tearing. In fascia, Golgi-like receptors provide feedback about extreme stretch or load, helping to adjust muscle tone and prevent injury. And Pacinian corpuscles. These receptors sense rapid changes in pressure and vibration. They are fast adapting, meaning they respond to sudden movements or oscillations. Pacinian corpuscles are found in deeper fascia, for instance in joint capsules and even in the visceral fascia. Their activation helps the body detect acceleration and deceleration of movement. If movement is too fast or abrupt, Pacinian stimulation can induce a quick relaxatory response in the muscles, a protective mechanism to avoid overshooting or injuring tissues. Think of how a sudden jolt might cause you to momentarily go limp. That's partly Pacinian-driven modulation. Ruffini endings. These are slow-adapting receptors that respond to sustained pressure, stretch, and shear forces in fascia. Ruffini endings abound in the aponeuroses and deep fascia layers. When you hold a stretch or a yoga pose, or when a therapist applies a slow melting pressure on a tight IT band, it's thought to stimulate Ruffini endings. Activation of Ruffini receptors has a calming effect. It decreases sympathetic nervous system activity, the fight or flight tone, and induces vagal parasympathetic responses. This results in muscle relaxation, lowered heart rate, and a general sense of calm in the body. Essentially, slow fascial work can trigger full body relaxation by way of Ruffini-mediated reflexes, a key rationale for slow massage, myofascial release, or gentle stretching techniques. Interstitial, free nerve endings. Fascia is loaded with free nerve endings, thin, unmyelinated nerves that serve various functions. Many are nociceptors, pain receptors, that signal when fascia is stretched too far or irritated. Others detect chemical changes, chemoreceptors, or temperature, thermoreceptors, in the tissue. These interstitial receptors contribute to our sense of interoception, the internal feeling of our body's state. For instance, the sense of discomfort from sitting too long in one position, or the feeling of a gentle stretch being pleasant or intense, involves these fascial nerve endings. Notably, fascia contains numerous C-fiber nerves, unmyelinated fibers associated with dull, aching pain and emotional tone, which ties fascia into the experience of pain and even emotion. Because of this rich innovation, fascia plays a critical role in proprioception, the sense of body position and movement, and in the perception of pain. When you close your eyes and touch your finger to your nose, thank your fascia. It's feeding your brain constant data about joint angles and muscle stretch. Conversely, if you feel a nagging, diffuse ache in your low back after a day of sitting, that too could be fascial, as slow build-up pain often originates in fascia. In fact, research shows that painful stimuli in fascia produce a different kind of pain than stimuli in muscles or skin. In one experiment, healthy volunteers were injected with saline to cause irritation in skin, in muscle, or in the thoracolumbar fascia of the back. The skin and muscle injections caused sharp, localized pain, whereas injection into the fascia produced a more diffuse, hard-to-pinpoint pain that radiated over a broader area. That finding is profound. It suggests that fascia is wired to produce pain that is felt as widespread or radiating. Many forms of chronic pain, like low back pain, fibromyalgia, or myofascial pain syndrome, have this fuzzy, broad character. It could be that unhealthy fascia is a major generator of such pain, more so than muscles or joints. Indeed, studies have found inflammation or thickening in the fascia of people with chronic pain. For example, patients with fibromyalgia show evidence of fascial inflammation, and people with chronic low back pain have been found to have denser fibrotic thoracolumbar fascia compared to healthy individuals, affecting its ability to slide. Fascial innervation also explains why problems in fascia can mimic or amplify muscle problems. A stiff muscle is often surrounded by tight fascia full of irritated mechanoreceptors. That area will have an exaggerated pain response due to the abundance of nociceptors in the fascia. In fact, connective tissue is much more richly supplied with pain sensors than muscle tissue, which is why fascia can cause intense pain even without muscle damage. Many cases of muscle strain or muscle soreness may actually be micro-injury and inflammation in the fascia surrounding the muscle. For instance, delayed onset muscle soreness, DOMS, after exercise, long attributed to tiny tears in muscle fibers, might involve the fascia too. Some researchers now suspect DOMS pain correlates with fascial injury or inflammation in the muscle's connective tissue. Given these revelations, some experts argue that fascia should be considered our largest sensory organ. Dr. Robert Schleip, a prominent fascia researcher, notes that fascia contains as many or more sensory nerves as the skin and is beyond any doubt our richest sensory organ in terms of providing internal body information. While not everyone is ready to label fascia a distinct organ, it's clear that our brain engages in an intricate conversation with fascia via these nerve endings, monitoring movement, tension, pressure, and pain across the body. This also means that by working with fascia, through movement, stretching, or manual therapy, we can directly influence the nervous system in powerful ways. More on that in sections ahead. Discovery of fasciocytes, a breakthrough in 2018. For many years, scientists assumed that the fibroblast cell was doing all the work of maintaining fascia, producing collagen, elastin, and the gel-like ground substance. Then, in 2018, a groundbreaking discovery showed that fascia has a surprise up its sleeve, a brand new cell type dedicated to lubricating fascia. This cell was discovered by Professor Carla Stecco, an anatomist and orthopedic surgeon at the University of Padua, Italy, and her colleagues, and she named it the fasciocyte. The announcement at the 2018 Fascia Research Congress in Berlin made waves in the scientific community. What exactly is a fasciocyte? Stecco's team found rounded, specialized cells nestled between layers of dense fascia. They studied the fascia lata of the thigh that were highly active in secreting hyaluronic acid, into the extracellular matrix. Hyaluronan, HA, is the slippery, viscous molecule that provides lubrication between fascia layers. It's what allows your muscles and fascia to glide over each other with low friction. The fasciocytes stained strongly for HA production and expressed specific enzymes, like HAS2 synthase, for making hyaluronan. They also had a distinct morphology under the electron microscope, different from ordinary fibroblasts. In short, Stecco had identified a cell whose primary job is to keep the fascial layers well lubricated and gliding. This discovery was significant for several reasons. A dedicated lubrication system. It showed the body invests cellular resources specifically for fascial gliding. Fasciocytes are essentially oil glands for our connective tissue, constantly secreting the HA that keeps fascia supple. Previously, we thought fibroblasts did this on the side, but fasciocytes appear to be the true HA factories. Mechanosensitivity. Stecco noted that fasciocytes respond to mechanical stimuli differently than fibroblasts. Her research suggests fasciocytes are stimulated by shear forces, whereas fibroblasts respond to tension and stretch. This means that sliding movements and sustained shearing, like wringing or twisting motions, might upregulate hyaluronan production by fasciocytes, improving fascial glide. By contrast, Tensile loading, like heavy stretching or strength training, influences fibroblasts to produce collagen. The two cells act somewhat like antagonists, one promoting slide, the other promoting stiffness, in a balanced way. This insight is leading clinicians to rethink exercise and manual therapy, perhaps incorporating more dynamic shearing motions, such as foam rolling, gentle oscillations, or certain forms of stretching, to specifically nourish the fascia's lubricant. Chart. Implications for pain and stiffness. Since hyaluronan is crucial for fascial movement, a dysfunction in fascia sites could lead to overly sticky fascia. Indeed, Stecco had earlier hypothesized that in myofascial pain syndromes, the hyaluronan between layers becomes less fluid and more adhesive, causing fascial layers to stick and tug, and that generates pain. Fascia sites give a direct target for this. Chronic inflammation or disuse might reduce fascia site activity, lowering HA production and causing adhesions. Conversely, therapies that stimulate these cells could restore proper gliding. In short, regulation of these cells could affect the functions of fasciae so they could be implicated in myofascial pain. The fascia site discovery, therefore, underscored that fascia is an active, self-maintaining organ. It's not just cables of collagen, it's alive, with its own cell population, ensuring it stays lubricated and functional. This finding also beautifully validates the idea that movement keeps our tissues healthy. Movement that creates shear, like back bending or a person doing a twisting exercise, likely stimulates fasciocytes to release more lubricant, literally oiling our insides. No wonder we feel stiff after being immobile. The lubrication dries up. On the flip side, steady movement hydrates our fascia. Many therapists use the phrase "motion is lotion." By engaging our muscles through a full range of motion, we create much-needed fascial shear, literally releasing oily lubricants deep within our bodies. Dr. Stecco's fascia sites gives us a cellular explanation for this phenomenon. Building on Dr. Carla Stecco's research, we now know that the health of fascia depends on both its collagen network and its hydration. Fascia sites, the specialized cells within fascia that produce hyaluronan, respond especially to shear forces, while mechanoreceptors embedded in the fascia respond to both pressure and stretch. Therefore, combining manual therapy that generates controlled, deep shearing forces with full range of motion exercise provides the dual benefit of stimulating fascial lubrication and reorganizing collagen. This combination not only breaks down adhesions mechanically, but also restores the tissue's natural viscosity and gliding properties, ensuring fascia remains supple and resilient. What we've learned is simple yet profound. Fascia is not just tissue, it is the hidden architecture of life. When it is nourished and cared for, fascia allows us to move with power and grace, to heal from strain, and to live without the burden of unnecessary pain. When neglected, it can silently bind us, limit us, and hold us back. By understanding fascia, and by working to keep it supple and resilient, we gain access to one of the most important pathways to lifelong health. This is the future of fitness and wellness, and it begins with fascia.